Your average LLM call can look fast, while P95 ruins the product. A delayed HTTPX hedge races only the stragglers and returns the first valid answer. You'll walk away with a setup that races a backup request, keeps the first valid answer, and measures the latency cost trade-off. I'm Professor Pi, teaching AI engineering and LLM systems with simple Python. Means hide pain. A tidy average fools dashboards, while a few slow responses make real users wait. In chat interfaces and assistants, those long tails are what people actually feel. Hedged requests are a targeted fix. If a call is slow, fire a short delay backup and accept whichever valid reply comes first. That trims your P95 without rewiring the whole system. You don't race every request, only the ones that linger. That keeps extra work limited for fast traffic. The trade-off is extra provider work on the unlucky slow calls. So you need a concrete way to measure latency improvement versus extra requests. Quick note, this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. First, we need a safe local LLM-style endpoint to test latency. That keeps experiments repeatable and cheap. This snippet builds a tiny HTTPX async client that behaves like a local LLM endpoint. Engineers often need a safe way to test latency behavior without burning tokens or hitting a live provider. FakeLLMTransport subclasses HTTPX async base transport, reads timing from request headers, sleeps for that duration, and returns an HTTPX response with a small JSON body. FakeLLMTransport stands in for a local LLM HTTP endpoint, so the demo is repeatable. The client variable is the shared httpx.async client the next steps we'll use. The output shows the active transport, proving the HTTPX path is wired before any hedge logic appears. Now confirm a single validated post works before we race anything. Hedging only makes sense if the basic call is correct and fails loudly on errors. This example sends one validated HTTPX post through the shared client. Before racing duplicate requests, the basic provider call has to be boring and dependable. Call LLM accepts a prompt plus small timing controls, sends client post to the LLM-style endpoint, and uses res.raise for status before trusting res.json. That status check matters because hedging should race valid provider responses, not silently accept an error body just because it arrived first. The MS value only controls the local transport delay for this demo. The output confirms the HTTPX post path returns one parsed answer. Next, measure the latency distribution so you know what to target. A few slow examples are the reason to hedge. This code turns a small latency sample into the tail latency signal that motivates hedging. Average latency can look acceptable, while a few slow LLM calls dominate timeouts and user-visible stalls. LatMS is the kind of sample you would normally collect around call LLM, and Quantiles calculates P95MS from the same list. Keeping average MS beside P95MS is useful because it shows why dashboards that only track the mean can miss the pain. Seeing a much larger P95 than the average is the practical trigger to try hedging. The output shows a healthy-looking average next to a much slower P95, which is the exact gap hedged request target. With that signal, add the hedge logic. We will wait briefly, then launch a duplicate call and take the first valid result. This snippet adds the core hedge. Wait briefly, then launch a duplicate HTTPX-backed call if the primary is still slow. The first task starts immediately through call LLM, and asyncio wait for gives it hedge after milliseconds to finish. Asyncio shield keeps that primary alive when the delay expires, so the second task can race it instead of replacing it. Once asyncio wait sees the first completed task, the loop cancels any pending loser to reduce wasted work. A smaller hedge after reacts faster but creates more duplicate calls. The output shows the hedge response won, and one unfinished task was cancelled. Finally, simulate rollout impact before flipping hedging on for all traffic. Quantify latency saved and extra requests paid for. This example quantifies the trade-off before turning hedging on for real traffic. The same primary MS sample is replayed as a small policy simulation. Fast calls stay single shot, while calls slower than hedge afterpay for a second request. Hedged MS estimates the visible latency after the duplicate can win, and calls records the cost multiplier. Increasing hedge after lowers extra cost, but lets more tail latency leak through. Decreasing it can improve P95 sooner, but duplicates more provider work. The output shows the latency saved at P95, alongside the added request cost, making the rollout decision measurable. This is a narrowly targeted hedge. Race only the slow calls, so most traffic stays single shot. Use it when occasional long LLM responses noticeably hurt user experience, but your average latency is fine. Remember that hedging increases provider usage for the hedged subset, so measure that cost as you tune. To go further, tune hedge after against real production query logs, and pick the point where P95 drops enough to matter, but duplicate rate stays acceptable. Run the simulation on a representative sample of your traffic, and iterate. If short, practical AI engineering helps, subscribe and watch the AI engineering videos.